Trace of matrix A. Trace of matrix A is nothing but sum of all diagonal elements. Properties. If A and B are square matrices of order, then trace of A plus B equal to trace of A plus trace of B. Trace of A minus B equal to trace of A minus trace of B. Trace of AB is not equal to trace of A into trace of B. Trace of BA is not equal to trace of B into trace of A. But trace of AB equal to trace of BA. Trace of KA equal to K into trace of A, where K is scalar. If A and B are diagonal matrices, then A plus B is a diagonal matrix, A minus B is a diagonal matrix, A square B square are also diagonal matrix, A power n plus or minus B power n small n belongs to capital N are diagonal matrices, A transpose is a diagonal matrix, A transpose plus or minus B transpose are diagonal matrices, adjacent A adjacent B are diagonal matrices, A inverse B inverse are diagonal matrices. What is a scalar matrix? If all the diagonal elements of a diagonal matrix are same or equal, then the matrix is called a scalar matrix. Thus a matrix A is a n by n is a scalar matrix. If A is equal to 0 for all I is not equal to j. Next, transpose of a matrix. Properties of a transpose. A transpose whole transpose equal to A plus or minus B whole transpose equal to A transpose plus or minus B transpose. Ka whole transpose equal to K into A transpose, where K is a scalar. AB whole transpose equal to B transpose into A transpose. A square whole transpose equal to A transpose whole square. Properties of symmetric and skew symmetric matrices. If A and B are symmetric matrices, then A plus or B minus B are symmetric. AB and BA need not be symmetric. AB plus BA is symmetric. AB minus BA is skew symmetric. A square B square comma A square plus or minus B square are symmetric. A cube A power 4 B cube B power 4 are symmetric. In general, A power K B power K are symmetric when K belongs to Ka is symmetric when K is scalar. If A and A transpose are any two square matrices, then A plus A transpose is symmetric. A minus A transpose comma A transpose minus A are skew symmetric. A into A transpose comma A transpose into A are symmetric. If A and B are skew symmetric, then A plus or minus B are skew symmetric. AB comma BA are not skew symmetric. AB comma BA are not skew symmetric. A square B square are symmetric. A square plus or minus B square are symmetric. A square A power 4 A power 6 are symmetric. A cube A power 5 A power 7 are skew symmetric. Ka is skew symmetric. Every square matrix A can be uniquely expressed as sum of symmetric and skew symmetric matrices as A equal to A plus A transpose numerator by 2 plus separate and brackets lo A minus A transpose as numerator by 2 is the denominator. So A equal to A plus A transpose by 2 plus A minus A transpose by 2. If A and B are square symmetric matrices, then AB is symmetric. AB equal to BA. If A and B are skew symmetric matrices, then AB is symmetric. A and B are commute. The matrix B transpose AB is symmetric or skew symmetric according as A is symmetric or skew symmetric. Order of O0 O n by n is skew symmetric as well as skew symmetric as well as n. In is symmetric. Positive integral powers of a square matrix. If A square matrix, if A is a square matrix, then the product of A into A is defined as A square and A cube idempotent matrix. If A square equal to A for a square matrix of A of order n, then A into A n by n is called an idempotent matrix. If AB equal to A and BA equal to B, then A and B are idempotent. If A is an idempotent matrix, then I minus A is also an idempotent matrix. If AB equal to BA equal to 0, then the sum of two idempotent matrix A and B is also an idempotent matrix. Involuntary matrix. If A square equal to In for a square matrix for A of order n, then matrix A is called an involuntary matrix. For example, the matrices A is an involuntary matrix that implies I plus A into I minus A equal to 0, nilpotent matrix. If there exists a positive integer m for a square matrix A of order n such that A power m equal to 0, then the matrix A is called a nilpotent matrix. If m is least positive integer for which A power m equals 0, then m is called the index of the nilpotent matrix. For example, A equals 0, 1, 0, 0 is a nilpotent matrix of index 2. Orthogonal matrix. A square matrix A n by n is said to be an orthogonal if A into A transpose equal to A transpose into A equal to I. A square matrix A n by n is said to be an orthogonal matrix if A into A transpose equal to A transpose into A equal to I, or A inverse equal to A transpose. For example, the matrices are orthogonal matrices. Note, if A and B are orthogonal matrices, then A, B and B are also orthogonal matrices. Conjugate matrix. If A equal to A is a given matrix, then the matrix obtained from a given matrix A by replacing all the elements by their corresponding conjugate complex numbers is called conjugate of matrix A and is denoted by A bar equal to A is A. Properties of conjugate matrix: A bar whole bar equal to A plus B whole bar equal to A bar plus B bar, AB whole bar equal to A bar B bar, K A bar whole bar equal to K A bar A bar, where K is any complex number. Transpose conjugate of a matrix: if A bar is a conjugate matrix of a complex matrix A, then A bar whole transpose is called transpose conjugate of A and is denoted by A power theta. A power theta equal to A bar whole transpose is nothing but A transpose whole bar. Properties: A per theta whole per theta equal to A plus B whole theta equal to A per theta plus B per theta, K A power theta equal to K bar A power theta, AB whole per theta equal to B per theta into A power theta. Hermitian matrix: a square matrix A equal to A is A is said to be Hermitian if A is A equal to A whole bar for all I comma j. The necessary and sufficient condition for matrix A to be Hermitian matrix is that A equal to A power theta. The diagonal element of a Hermitian matrix are purely real. A equal to 2 plus 3A, 2 minus 3A, 3 is a Hermitian matrix. Skew Hermitian matrix: a skew Hermitian matrix A equal to A is said to be skew Hermitian matrix if A is equal to minus AJI minus AJI whole bar for all I comma j. The necessary condition for and sufficient condition for a matrix A to be skew symmetric is that skew Hermitian is that A power theta equal to minus A. The diagonal elements of a skew Hermitian matrix are either 0 or purely imaginary. For example, A equal to 2i 4 plus 3i 2 minus 5i and so on is a skew Hermitian matrix. A equal to 2i 4 plus 3i 2 minus 5i minus 4 minus 3 0, 3 plus 4i minus 2 plus 5i minus 3 minus 4i 0. Every complex square matrix A can be uniquely written as a sum of Hermitian and skew Hermitian matrices. Unique matrix: a matrix, a complex matrix A is said to be unitary matrix. Unitary matrix: a complex matrix A equal to A is said to be unitary if A into A power theta equal to A power theta into A equal to I, or A power theta equal to A inverse. Properties of unitary matrix: if A is unitary, then A transpose is also unitary. If A and B are unitary matrices, then AB is also unitary. Periodic matrix: a square matrix is said to be periodic if A power k plus 1 equal to A. If k is the least positive integer for which A power k plus 1 equal to A, then k is said to be period of A. If A is a real square matrix, then A into A transpose is B, always symmetric. If A an n by n array V is defined as follows: Vi is equal to I minus A for all I comma j, 1 less than or equal to I, j less than or equal to n, then sum of the elements of the array V is answer is 0. The number of different n by n and symmetric matrices with each element being either the number of different n by n symmetric matrices with each element being either option is C, 2 power n square plus n by 2 అంటే 2 పవర్ మిగతా వచ్చేదంతా పై న్యూమరేటర్లో ఉంది, పవర్లోనే ఉంది, n square plus n by 2. దీన్ని ఎలా చేయొచ్చు అంటే టోటల్ నెంబర్ ఆఫ్ ఎలిమెంట్స్ ఇన్ n by n matrix equal to n square. In a symmetric matrix A is A equal to AJ. To count different n by n symmetric matrices, we count the number of ways to fill the elements in the diagonals and elements above the diagonals. Number of diagonal elements equal to n. Number of non-diagonal elements equal to n square minus n. Number of elements in the diagonal plus non-number of elements above the diagonal equal to n plus n square minus n by 2 equal to n square plus n by 2 equal to n into n plus 1 by 2. Now each of these elements can be either 0 or 1. The total number of the ways we can fill is 2 power n into n plus 1 by 2. Algebra of matrices. Okay, now addition of matrices is associative. A plus B plus C equal to A plus B plus C. Commutative: A plus B equal to B plus C. Existence of the additive inverse: for any given matrix A and there exists a matrix minus A such that A plus of minus A equal to 0. Cancellation law holds good in case of addition of matrices. Left cancellation law and right cancellation law. multiplication of matrices and all, you know. Properties of determinants. If A and B are two square matrices of the same order, then AB equal to determinant of A and determinant of B. Determinant of A power m equal to determinant of A whole power m. Determinant of A inverse equal to 1 by det A. If every element of a row or column of a determinant of A is 0, then det A equal to 0. If A is a square matrix of order n, then det A equal to A transpose of det. If any two rows or columns of a determinant are identical, then the value of determinant is 0. If the corresponding elements of any two rows of a determinant are proportional, then the value of the determinant is 0. If any two rows of a determinant are interchanged, then the sign of determinant changes. If each element of a row of a determinant is multiplied by constant k, then the value of the determinant will be multiplied by k, or the value of the new determinant is the k times the value of the original determinant, for example 27k. If each element of a row or column of a determinant is multiplied by the same constant k and added to the corresponding elements of some other row, then the value of the determinant remains same, for example 1 plus 2 3 plus 3 1 plus 4k 2 plus 5k 3 plus 6k. In the determinant on the right side, first row is obtained with operation r1 tends to r1 plus k r2. Both are same. Each element of a row of a determinant is expressed as the sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. Okay, the determinant of a upper triangle or lower triangle diagonal scalar or unit matrix is equal to product of its diagonal elements. If A is an orthogonal matrix of order n, then determinant of A equal to plus or minus 1. If A is a unitary matrix of order n, the determinant of A equal to plus or minus 1. A bar whole transpose A bar equal to determinant of A power theta equal to determinant of A bar. The determinant of Hermitian matrix is always a real number. If A is an idempotent matrix, then determinant of A equal to 0 or 1. Determinant of In equal to 1. The determinant of a skew symmetric matrix of odd order is 0. If A equal to is a square matrix of order n, then the number of products of the elements of any row column with their cofactors is always equal to determinant of A or det A. If A equal to A is a square matrix of order n, then sum of the products of elements of any row or column with the cofactors of the corresponding elements of some other row is 0. Adjoint matrix B n by n is a cofactor matrix of n by n. Then the adjoint matrix of n by n is denoted by adjoint of A and is defined as B transpose adjoint of A equal to B transpose. Properties of adjoint matrix. If A is a square matrix of order n, then A into adjoint A equal to adjoint A into A equal to det A into In. If 0 is a zero matrix of order n, then adjoint of 0 equal to 0. If In is a unitary matrix of order n, then adjoint of In equal to In. If D is a diagonal matrix of order n, then adjoint of D is also a diagonal matrix. If A is a square matrix of order n, then adjoint of A transpose equal to adjoint A whole transpose. Adjoint A మొత్తానికి ట్రాన్స్పోజ్ వస్తుంది. If A and B are non-single matrices, then adjoint of AB equal to adjoint of B into adjoint of A. If A or B is a single matrix, then adjoint of AB equal to adjoint of B into adjoint of A. If A and B are non-single matrices, then adjoint of AB equal to adjoint of B into adjoint of A. If det A equal to 0, then adjoint of A determinant also equal to 0. If A is a square matrix of order n, then determinant of adjoint A equal to det A power n minus 1. If A is a non-single matrix of order n, then adjoint of A equal to det A power n minus 2 into A. If A is a square matrix of order n, then determinant of adjoint A equal to determinant of A whole power n minus 1 whole square. If A is a square matrix, then adjoint of A times A power theta equal to adjoint of A whole power theta. If A is a Hermitian matrix, then adjoint of A is also Hermitian. If A is a symmetric matrix, then adjoint of A is also symmetric. If A equal to ABCD, then adjoint of A equal to D minus B minus C minus C. D minus B minus C A, singular matrix. A square matrix A of order n is said to be the singular matrix if determinant of A n by n equal to 0. Non-singular means determinant of A n by n is not equal to 0. Okay, now inverse or reciprocal of a square matrix. If the inverse of square matrix exists, then the matrix is called invertible matrix. If A is a non-single matrix of order n, then A inverse equal to 1 by det A into adjoint A. That means A inverse equal to adjoint A by det A. Properties of inverse of a square matrix. The necessary sufficient condition for a square matrix A to possess half the inverse is the that A is not equal to 0. That is non-single matrix. If the inverse of a matrix A exists, then it is unique. If A, B, C are non-single matrices, then AB whole inverse equal to BA, B inverse, A inverse, reversal law. ABC whole inverse equal to C inverse, B inverse, A inverse. If A is non-single matrix of order n, then A transpose whole inverse equal to A inverse whole transpose and A power theta whole inverse equal to A inverse whole power theta. If A is non-single and symmetric matrix, then A inverse is also symmetric matrix. If AB equal to BA for two non-single matrices, then A inverse B inverse equal to B inverse A inverse. Cancellation law. If A is non-single matrix of order n and B C are square matrices of same order as A, then AB equal to AC equal to, that implies B equal to C. BA equal to CA equal to, that implies B equal to C. If the product of two non-zero square matrices is zero matrix, then both A and B must be single matrices. If A and B are n-rowed square matrices such that AB equal to 0 and B is non-single matrix, then A equal to 0. If A is an idempotent matrix and A is not equal to I, then A is singular. If A is orthogonal matrix, then A transpose and A inverse are also orthogonal. If A equal to ABCD and K is scalar, then KA whole inverse equal to 1 by K A inverse. The determinant of skew symmetric matrix of odd order is 0. If A 0 0 0 BC 0 0 C such that det A is not equal to 0, then A inverse equal to 1 by A 0 0 0 1 by B 0 0 0 1 by C. In inverse equal to In. Linear combination of vectors. If x1, x2 and so on xr are vectors of order n, then k1, k2 and so on are scalars, then expression of form k1 x1 plus k2 x2 and so on kr xr is also a vector, and it is called linear combination of the vectors x1, x2 and so on xr. Linear dependent vectors. The vectors x1, x2 and so on xr of same order n are said to be linear dependent if there exist scalars or numbers k1, k2 and so on kr, not all such that k1 x1 plus k2 x2 and so on kr xr equal to 0, where O denotes the zero vector of order n. Linearly independent vectors. The vectors x1, x2 and so on xr of same order n are said to be linearly independent vectors if every relation of the type k1 x1 plus k2 x2 and so on kr xr equal to 0. That implies k1 equal to k2 equal to and so on kr equal to 0. If x1, x2 and so on xr linearly dependent vectors, then at least one of the vectors can be expressed as a linear combination of other vectors. If A is a square matrix of order n and at A equal to 0, then the rows and columns are linearly dependent. If A is a square matrix of order n and at A is not equal to 0, then the rows and columns are linearly independent. Any subset of a linearly independent set is itself a linearly independent set. If a set of vectors includes a 0 vector, then the set of vectors is a linearly dependent set. Inner product x y x transpose y is inner product. X transpose y equal to y transpose x, that is inner product is symmetric. X dot y equal to 0, then vectors x and y are perpendicular. X dot y equal to plus or minus 1, the vectors x and y are parallel. Length or norm of a vector, if x equal to x1, x2 and so on, length equal to root x into x, that equal to root of x1 square plus x2 square and so on xn square. Then x equal to root of 1 square plus 2 square plus 3 square equal to root 9 equal to 3. Unit vector or normal vector. A vector x is said to be a unit vector if length equal to 1. Length equal to 1. Okay. Orthogonal vectors. The two vectors x1, x2 are said to be orthogonal if x1, x2, if x1 transpose x2 equal to x2 transpose x1 equal to 0. Orthogonal set. The column vectors x1, x2 and so on of same order are said to be orthogonal if xi, xj transpose equal to xi transpose xj equal to 0. Orthonormal vectors. The vectors x1, x2 and so on xm of order said to be orthonormal if xi transpose xj equal to 0 for all I is not equal to 0 equal to 1 for all I equal to 0. I equal to j for all I equal to j nana I equal to j. The orthonormal vectors x1, x2 and so on x set to be form an orthonormal system. If a matrix A of order is said to be an orthonormal matrix, then its rows and columns are orthonormal vectors. If a matrix of order n is an orthogonal matrix, then its rows and columns form an orthonormal system or orthonormal vectors. These are called orthonormal vectors. Very, very important. Rank of a matrix. A non-negative integer R is said to be the rank of matrix A if there exists at least one non-integer minor of order, or all minors of order or R plus 1. If they exist are zeros, then we can write it rank of A equal rank of A equal to R. Rank of a matrix A equal to the order of any largest non-vanishing minor of A. Rank of a matrix A, the number of linearly independent rows of A equal to the number of linearly independent columns of A. A necessary and sufficient condition that vectors x1 equal x1, x11, x12 and so on, x1m, x2 linearly independent is that rank of A equal to n. Linearly dependent is that rank of A is not equal to n. If A is a matrix of order m by n and rank of A equal to R, then the maximum number of linearly independent rows or columns of A is R. Note, rank of a matrix is 0 if A is a null matrix. If A is not equal to 0, then rank of A is greater than or equal to 1. If A m by n is not equal to 0, then rank of A m by n is less than or equal to minimum of m comma n. If determinant of A n by n is not equal to 0, then rank of A n by n equal to n. If determinant of A n by n equal to 0, then rank of A n by n is less than n. Rank of A n equal to n. Rank of A equal to rank of A transpose. Rank of A b less than or equal to minimum of rank of A comma rank of B. Rank of A plus b less than or equal to rank of A plus rank of B. Rank of A minus b less than greater than or equal to rank of A minus rank of B. The rank of a diagonal matrix is equal to the number of non-zero diagonal elements. Number of non-zero diagonal elements. Echelon form. A matrix A of order n by n is said to be in the row echelon form if 0 rows, if any occur, then they must be below the non-zero rows. The number of zeros before the first non-zero element in each row is less than the number of zeros in the next row. If a matrix of order m by n is in echelon form, then rank of A m by n equal to number of non-zero rows in A. Note, rank of a matrix will not be affected by the applying the elementary transformations. To find rank of a matrix, we have to reduce the matrix A into its echelon form using only elementary row transformations. Then rank of A equal to number of non-zero rows in the echelon form of A. The echelon form of A. System of linear equations, non-homogeneous system of linear equations. The system of m non-homogeneous linear equations in n variables x1, x2 and so on xn is given by a1 on x1 plus a1 to x2 and so on, a1 and xn equal to b1, a2 on x2, x1 plus a2 to x2 plus and so on, a2 to n xn equal to b2. Then the set of these equations can be written in the form ax equal to b, where a is the coefficient of matrix, x is the column matrix of the variable, and b is the column matrix of constants b1, b2 and so on, bn. The system of linear equations ax equal to b has a solution are consistent if and only if rank of A equal to rank of A bar B. Theorem. The system Ax equal to B has a unique solution if and only if rank of A equal to rank of A bar B equal to number of variables. Infinitely many solutions equal to rank of A equal to rank of A bar B is less than number of variables, and no solution inconsistent if rank of A is not equal to rank of A bar B, that is rank of A is less than rank of A bar B. Homogeneous system of linear equations. If the system of m homogeneous linear equations and variables x1, x2 and so on xn is given by a1 on x1 plus a1 to x2 plus and so on, a1 xn equal to 0, a2 on x1 plus a2 to x2 plus and so on, a2 and xn equal to 0, then the set of these equations can be written in the matrix form as ax equal to 0, where a is the matrix of the quotients and x is the column matrix of the variables. Theorem. The system ax equal to 0 has unique solution, zero solution, and trivial solution if rank of A equal to number of variables n, and if infinitely many non-zero or non-trivial solutions if rank of A is less than n. Note, in the system of homogeneous linear equations x equals 0 if A is the square of matrix and determinant of A is not equal to 0, then system possesses only trivial solutions, that is zero solution or unique solution. If that A equal to 0, then the system possesses infinitely many non-trivial solutions, that is non-zero solutions. If rank of A equal to R and number of variables equal to n, then the number of linearly independent solutions of Ax equal to 0 is the n minus R. In a system of homogeneous linear equations, if the number of unknowns or variables exceeds the number of equations, then the system necessarily possesses a non-zero solution. eigenvalues, eigenvectors, and Cayley-Hamilton theorem. Let A be a square matrix of order n and lambda be a scalar. Determinant of A minus lambda equal to 0 is called characteristic equation of A. The roots of characteristic equation are called eigenvalues, or characteristic roots are latent roots of A corresponding to each eigenvalue lambda. There exists a non-zero vector x such that Ax equal lambda x, A minus lambda A into x equal 0. Hence lambda x is called as eigenvector, characteristic equation, or latent vector of A. Properties of eigenvalues for lower triangular matrix, upper triangular matrix, or diagonal matrix. The eigenvalues are same as diagonal elements of the matrix. If lambda 1 and so on lambda n are eigenvalues of matrix A of order n, then lambda 1 plus lambda 2 and so on lambda m equal to trace of A. Lambda 1 into lambda 2 and so on lambda n is the equal determinant of A. 0 is an eigenvalue of matrix A if and only if A is singular. If all the eigenvalues of A are non-zero, then A is non-singular. If lambda is an eigenvalue of matrix A and k is an scalar, then lambda power m is eigenvalue of matrix A power m. K lambda is an eigenvalue of matrix K. Lambda plus k is an eigenvalue of matrix A plus K. Lambda minus k is an eigenvalue of matrix A minus K. A naught plus A1 lambda plus A2 lambda square is the eigenvalue of matrix A naught I plus A1 A plus A2 square A2 A square. For example, if lambda is an eigenvalue of non-singular matrix A, then 1 by lambda is the eigenvalue of A inverse, and that A by lambda is the eigenvalue of adjoint A. The eigenvalues of A and A transpose are same. If lambda is an eigenvalue of the orthogonal matrix, then 1 by lambda is also another eigenvalue of same matrix A. If A plus root b is an eigenvalue of a real matrix A, then A minus root b is also other eigenvalue of matrix A. If A plus b ib is an eigenvalue of matrix real matrix A, then A minus ib is also other eigenvalue of A. The eigenvalues of real symmetric Hermitian matrix are always real, and the eigenvalues of real skew symmetric or skew symmetric or skew Hermitian, real skew symmetric or skew Hermitian matrix are either 0 or purely imaginary. The eigenvalues of an orthogonal or unitary matrix are of unit modulus. Properties of eigenvectors. Lambda is an eigenvalue of matrix A. There exists a non-zero vector x such that Ax equal to lambda x. For each eigenvalue of matrix A, there are infinitely many eigenvectors. If x is an eigenvector of matrix A corresponding to the eigen lambda, then kx is also an eigenvector of A corresponding to the same eigenvalue of lambda. If x is an eigenvector of matrix A, then x cannot correspond to more than one eigenvalue A. That is, we cannot get some same eigenvector for two different eigenvalues of matrix A. If some eigenvalues of matrix A are repeated, then the eigenvalues of A may or may not be linearly independent. If lambda 1 and so on lambda m are distinct eigenvalues of A square matrix A of order m, then the corresponding eigenvectors x1 and so on xn of A matrix are linearly independent. The eigenvectors of A and A per m are same. The eigenvectors of A and A minus A inverse are same. The eigenvectors of A and rank of A equal to A naught I plus A1 A plus A2 A square are same. The eigenvector of A and K are same. The eigenvectors of A and A transpose are not same. Eigenvectors of a symmetric matrix are orthogonal. Algebraic multiplicity of an eigenvalue. If an eigenvalue of lambda of a matrix A of order n is repeated m times, then the number m is called algebraic multiplicity of an eigenvalue lambda. Geometric multiplicity of an eigenvalue. If the number p is the number of linearly independent eigenvectors of matrix A of order n corresponding to an eigenvalue lambda, then p is called geometric multiplicity of lambda, and it is given by p equal to n minus r equal to number of variables minus rank of A minus lambda I. The geometric multiplicity of an eigenvalue cannot exceed its algebraic multiplicity. Cayley-Hamilton theorem. If the skew matrix satisfies its own characteristic equation, that means Cayley-Hamilton theorem, we have suppose lambda cube minus 12 lambda square plus 36 lambda minus 32 is equal to 0 is characteristic equation. Then Cayley-Hamilton theorem, we have substitute A square. Application of Cayley-Hamilton theorem. Two important applications of theorem are to find higher powers of matrix A, to find the inverse matrix of A. Diagonalization matrix. If for a given matrix square matrix of order n, there exists a non-singular matrix of P such that P inverse AP equal to D. AP equal to PD, where D is a diagonal matrix, then A is said to be diagonalizable matrix. Note, if x1, x2 and so on linearly dependent eigenvectors of A 3 by 3 corresponding to eigenvalues lambda 1 and to lambda 3, then P can be found such that P inverse AP equal to D or AP equal to PD. If A is a diagonalizable matrix of order n by n, then A power k equal to P D power k into P inverse, and D power k equal to P inverse A power k into P. P inverse A power k into P. Minimum polynomial. If f of A equal to 0, then we say that the polynomial f of x annihilates the matrix A. A polynomial in x in which the coefficient of the highest power x is unity is called monic polynomial. The monic polynomial of lowest degree that annihilates a matrix A is called the minimum polynomial of A. Note the minimal polynomial of a matrix A divides the characteristic polynomial of A. The characteristic polynomial and minimal polynomial of matrix A have the same irreducible factors if lambda is an eigenvalue of matrix A, if and only if lambda is the root of the minimal polynomial of A. Standard limits. Limit extends to A x power n minus a power n whole by x minus a equal to n into a power n minus 1. Limit extends to 0 e power mx separate ga minus 1 e power mx minus 1 and numerator denominator x aithe equal to m. Limit extends to 0 a power x minus 1 a power x where 1 where that is the numerator part, a power x minus 1 is the numerator part, denominator part x ante limit extends to 0 a power x minus 1 by x equal to log a base c. Limit extends to 0 1 plus ax whole power 1 by x equal to a power a. Limit extends to infinity 1 plus a by x whole power x equal to e power a. Limit extends to 0 sin x by x equal to limit extends to 0 tan x by x equal to 1. Limit extends to infinity sin x by x equal to 0. Limit extends to infinity a power x plus b power x whole by 2 whole power 1 by x equal to root ab. Limit extends to infinity limit extends to 0 cos x plus a sin bx whole power 1 by x equal to e power ab. Limit extends to 0 numerator part 1 minus cos ax denominator part x square. That means limit extends to 0 1 minus cos ax by x square equal to a square by 2. Now standard derivatives. D by dx of uv equal to u into dv by dx plus v into du by dx. D by dx of u by v equal to v into du by dx minus u into dv by dx by v square. D by dx of a power ax equal to a power x into log a base c. D by dx of log x base c equal to 1 by x. D by dx of log x base a equal to 1 by x into log e base a. D by dx of log x base a equal to 1 by x into log e base a. D by dx of sin x equal cos x. D by dx of cos x equal minus sin x. D by dx of tan x equal secant square x. D by dx of cot x equal minus cos x square x. D by dx of sec x equal secant x tan x. D by dx of cosecant x equal minus cosecant x cot x. D by dx of sin inverse x equal to root of 1 by root of 1 minus x square. D by dx of cos inverse x equal to minus 1 by root of 1 minus x square. D by dx of tan inverse x equal to 1 by 1 plus x square. D by dx of cot inverse x equal to minus 1 by 1 plus x square. D by dx of secant inverse x equal to 1 by x into root of x square minus 1. D by dx of cosecant square inverse x equal to minus 1 by x into root of x square minus 1. D by dx of sin hx equal cos hx. D by dx of cos hx equal sin hx. Okay, now if f of x is differentiable at x equal to a, then the Taylor series expansion of f of x about the point x equal to a is given by f of x equal to f of a plus x minus a into f dash a plus x minus a whole square by 2 factorial f double dash a and x and so on x minus a whole power n by n factorial f power n of a and so on. If we choose a equal to 0, we get f of x equal to f of 0 plus x into f dash of a plus x square by 2 factorial f double dash of 0 and so on f per n by n factorial f n per 0. This is called a Taylor series expansion about x equal to 0. Taylor series about origin is called as Maclaurin series. If f of x is not differentiable at x equal to a, then f of x cannot be expressed as Taylor series in power of x minus a. Some standard forms: 1 minus x whole inverse equal to 1 plus x square plus x cube. 1 plus x whole inverse equal to 1 minus x plus x square minus x cube and so on. 1 minus x whole power minus 2 equal to 1 plus 2x plus 3x square plus 4x cube. 1 plus x whole power minus 2 equal to 1 minus 2x plus 3x square minus 4x cube. 1 minus x whole power minus 3 equal to 1 plus 3x plus 6x square plus 10x cube. 1 plus x whole power minus 3 equal to 1 minus 3x plus 6x square minus 10x cube. 1 plus x whole power n equal to 1 plus nx plus n into n minus 1 by 2 factorial x square plus n into n minus 1 into n minus 2 into by 3 factorial x cube and so on. 1 minus x whole power minus n equal to 1 plus nx plus n into n plus 1 by 2 factorial x square plus n into n plus 1 into n plus 2 by 3 factorial x cube and so on. E power x equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. E power minus x equal to 1 minus x plus x square by 2 factorial plus x cube by 3 factorial and so on. Sin x equal to x minus x cube by 3 factorial plus x power 5 by factorial minus x power 7 by 7 factorial and so on. Sin hx equal to x plus x cube by 3 factorial plus x power 5 by 5 factorial plus x power 7 by 7 factorial and so on. Sin inverse x equal to x plus 1 by 2 x cube by 3 plus 7 half 3 by 4 x power 5
by 5 plus half 3 by 4 5 by 6 x power 7 by 7 and so on. Cos x equal to 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial and so on. Cos hx equal to 1 plus x square by 2 factorial plus x power 4 by 4 factorial plus x power 6 by 6 factorial and so on. Cos inverse x equal to pi by 2 minus sin inverse x equal to pi by 2 minus half x plus 1 half x cube by 3 plus half 3 by 4 x power 5 by 5. Tan x equal to x plus x cube by 3 plus 2 x power 5 by 15. Tan hx equal to x minus x cube by 3 plus 2 x power 5 by 15. Tan inverse x equal to x minus x cube by 3 plus x power 5 by 5 minus x power 7 by 7 minus 1 to 1 అయితే అదే pi by 2 minus 1 by x plus 1 by 3 x cube minus 1 by 5 x power 5 x greater than equal to 1 pi plus 1 by x minus 1 by 3 x cube plus 1 by 5 x power 5 x less than 1. Cot x equal to 1 by x minus x by 3 minus x cube by 45 and so on. Cot hx equal to 1 by x plus x by 3 minus x cube by 45 and so on. Cot inverse x equal to pi by 2 minus tan inverse x. Secant x equal to 1 plus x square by 2 plus 5x power 4 by 24 and so on. Cosecant x equal to 1 by x plus x by 6 plus 7x cube by 360 and so on. Natural log 1 plus x equal to x minus x square by 2 plus x cube by 3 minus x power 4 by 4 and so on. The x should be minus 1 to 1 in the range. Partial and total derivatives. Partial derivatives, if u equal to f of x y is a function on x and y, then dou u by dou x equal to limit to 0 f x plus y minus f of x y by h equal to uk ux. Dou u by dou y equal to limit k tends to 0 f of x comma y plus k minus f of x y by k equal to uy. Similarly, higher order derivatives dou square u by dou x square comma dou square u by dou y square, dou square u by dou x dou y, dou square u by dou y dou a can be obtained. Okay, now homogeneous function. A function is said to be homogeneous if degree of each and every term in the function is same. X square yz minus 3yz cube is a homogeneous function with a degree 4. Log of x square by y is a non-homogeneous function. Cos inverse of x plus y by x minus y is a homogeneous function with degree 0. Then Euler's theorem, if u equal to f of x y is a homogeneous function with a degree n in x and y, then n into ux, x into ux plus y into uy equal to nu. Second point, x square uxx plus 2xy uxy plus y square uyy equal to n into n minus 1 into u. Corollary, if u equal to f of x y z is a homogeneous function with a degree n in x comma y comma z, then x into ux plus y into uy plus z into uz equal to nu. X square ux plus y square uyy plus z square uzz plus 2xy uxy plus 2yz uyz plus 2xz uxz equal to n into n minus 1 into u. If u equal to uxy is a non-homogeneous function but f of u is a homogeneous function of degree n in x and y, then x into ux plus y into uy equal to n into f of u, the numerator part, denominator part by f dash u, n into f of u by f dash u equal to g of u. X square ux plus 2xy uxy plus y square uyy equal to g of u into g dash of u minus 1. If u equal to fxy plus g of xy plus h of xy, where f, g, h are homogeneous functions of degree m and p respectively, then xux plus yuy equal to m of plus ng plus ph. X square uxx plus 2xy uxy plus y square uyy equal to m into m minus 1 into f plus n into n minus 1 into g plus p into p minus 1 into h. Maxima and minima. Maxima and minimum for functions of one variable. Local or relative maximum. A function f of x is said to have a maximum at x equals c if there exists delta greater than 0 such that modulus of x minus c less than delta, that implies f of x less than or equal to f of c. Local or relative minimum. A function f of x is said to be have a minimum at x equals c if there exists delta greater than 0 such that modulus of x minus c less than delta, that implies f of x greater than or equal to f of c. Stationary points. The value of x for which f dash x equals 0 are called stationary points or turning points. Stationary values if a function f of x is said to be stationary at x equal to a if f of f dash f a equal to 0 and f of a is stationary value. Extreme point. The point at which the function has a maximum or minimum is called extreme point. Extreme values. The values of the function at extreme points are called extreme values. Points of inflection. The point at which a curve crosses its tangents is called point of inflection. The function of f of x has neither maximum nor minimum at point of inflection. In SR condition, for a function to have an extreme value at x equal to a is f dash a equal to 0. If f dash a equal to 0 is only a necessary condition but not sufficient condition for f of a to be extreme value of f of x. For the function f of x equal to x cube, f of 0 is not an extreme value even though f dash a equal to 0. If f of 0 is minimum value of f of x equal to modulus f x, even f dash 0 does not exist. Absolute or global, maximum or minimum. Working value to find maximum, let f of x be a function, find f dash fx equal to f dash fx to 0 to obtain the stationary points. If f double dash x, find f double dash x of x at each stationary point. If f double dash of x not greater than 0, then f of x has a minimum at x equal to x naught. If f double dash x naught is less than 0, then f of x has a maximum at x equal to x naught. If f double dash of x not equal to 0, then f of x may or may not have extremum. In this case, check for maximum and minimum using the changes in sign of f dash of x as given below. For f x less than x naught, if f dash of x less than 0, and x greater than x naught, if f dash of x greater than 0, then f of x is a minimum value of f of x. Maximum and minimum for functions of variables. Let z equal to f of xy be the function of two variables for which maximum or minimum is to obtained. Let p equal to dou z by dou x, q equal to dou z by dou y, r equal to dou square z by dou x square, s equal to dou square z by dou x dou y, t equal to dou square z by dou y square. Working rule: find p, q, r, s and t. Equate p and q to 0 for obtaining stationary points. Find r, s and t at each stationary point. If rt minus s square greater than 0 and r greater than 0, then f of xy has a minimum at that stationary point. If rt minus s square greater than 0 and r less than 0, then f of xy has a maximum at that stationary point. If rt minus s square less than 0, then f of x comma y has no extremum at that stationary point, and such points are called saddle points. If rt minus s square equals 0, then case is undecided. Mean value theorem of integrals. If function f of x is continuous on a comma b, then there exists a real number c in a comma b such that integration of a comma b f of x dx equal to b minus a into f of c. Here the average value or the mean value of an integral function of x defined on a comma b is given by 1 by b minus a integration of a to b f of x dx equal to f of c. Standard integrals. Integration of dx equal to x, integration of x power n dx equal to x power n plus 1 by n plus 1, integration of 1 by x dx equal to log x by c, integration of e power x dx equal to e power x, integration of log x dx equal to x into log x minus 1. Log x minus 1 is the one term, x whole of log x minus 1. Integration of a power x dx equal to a power x by log a by c. Integration of sin x dx equal to minus cos x. Integration of cos x dx equal to sin x. Integration of tan x equal to minus log cos x into equal to log secant x. Integration of cot x dx equal to log sin x. Integration of secant x dx equal to log of secant x plus tan x equal to log of tan of x by 2 plus pi by 4. Integration of cosecant x dx equal to log of cosecant x minus cot x log of tan of x by 2. Integration of secant square x dx equal to tan x. Integration of cosecant square x dx equal to minus cot x. Integration of secant x tan x dx equal to secant x. Integration of cosecant x cot x dx equal to minus cosecant x. Integration of dx by a square plus x square equal to 1 by a tan inverse of x by a equal to minus 1 by a cot inverse of x by a. Integration of dx by a square minus x square equal to 1 by 2a log of a plus x by a minus x. Integration of dx by x square minus a square equal to 1 by 2a into log of x minus a by x plus a. Integration of dx by a square minus x square equal to sin inverse of x by a equal to minus cos inverse of x by a. Integration of dx by root of a square plus x square dx equal to sin h inverse of x by a equal to log of modulus of x plus root of a square plus x square. Integration of dx by root of x square minus a square dx equal to cos h inverse of x by a equal to log of mod of x plus root of x square minus a square. Integration of 1 by x into root of x square minus 1 dx equal to secant inverse x equal to minus cosecant inverse x. Integration of root of a minus x square minus x square dx equal to x by 2 into root of a square minus x square plus a square by 2 into sin inverse of x by a. Integration of root of a square plus x square dx equal to x by 2 into root of a square plus x square plus a square by 2 into sin h inverse of x by a. That equal to x by 2 into root of a square plus x square plus a square by 2 into log of modulus of x plus root of a square plus x square. Integration of root of x square minus a square dx equal to x by 2 into root of x square minus a square by 2 into cos h inverse of x by a. That equal to x by 2 into root of x square minus a square by 2 log of modulus of x plus root of x square minus a square. Integration of e power x sin bx dx equal to e power ax by a square plus b square into అదొక టర్మ్ ఇంటూ a sin bx minus b cos bx. Integration of a e power x cos bx dx equal to e power ax by a square plus b square into a cos bx plus b sin bx. Integration of sin hx dx equal to cos hx dx. Integration of cos hx dx equal to sin hx. Integration of u of x dx equal to u of x into integration of v of x dx minus integration of u dash x into integration of v of x dx into dx. Integration of a to b f of x dx equal to integration of a to b f of b f of a dy. Integration of a to b f of x dx equal to minus integration of b to a f of x dx. If a less than c less than b, then integration of a to b f of x dx equal to integration of a to c f of x dx plus integration of c to b f of x dx. Integration of 0 to a f of x dx equal to integration of 0 to a f of a minus x dx. Integration of 0 a to b f of x dx equal to integration of a to b f of a plus b minus x dx, and integration of a to b f of x by whole by f of x plus f of a plus b minus x dx equal to b minus a by 2. Integration of minus a to a f of x dx equal to integration of 0 to f of x dx if f of x is an even function equal to 0. If f of x is an odd function, integration of 0 to f of x dx equal to 2 integration of 0 to a by 2 f of x dx if f of a minus x equal to f of x equal to 0. If f of a minus x equal to minus f of x, integration of 0 to n f of x dx equal to n into integration of 0 to f of x dx if f of x plus a equal to f of x, that is f of x is a periodic function with period a. Integration of 0 to x 0 to a x into f of x dx equal to a by 2 integration of 0 to f of x dx if f of a minus x equal to f of x. Integration of 0 to b f x into f of x dx equal to a plus b by 2 integration of 0 to a 0 integration of a to b f of x dx if a plus b minus x equal to f of x. Integration of 0 to pi by 2 sin power n x dx equal to integration of 0 to pi by 2 cos power n x dx, that equal to n in 10 minus 1 by 2, n in 10 minus 1 by n in n minus 3 by n minus 2, n minus 5 by n minus 4, and so on 2 by 3 if n is odd, n in n minus 1 by n minus 3 by n minus 2, n minus 5 by n minus 4, and so on 1 by 21 pi by 2 if n is even. 0 to pi by 2 sin power mx into cos power nx dx equal to numerator part m minus 1 into m minus 3 into m minus 5 and so on to r1 into n minus 1 into n minus 3 and so on to r1. Denominator part m plus n minus 2, m plus n minus 4 and so on to r1, where k equal to pi by 2 if m and n are even equal to 1. Otherwise, integration of minus a to a f of x dx equal to integration of 0 to a f of x dx plus 0 to a f of minus x dx. Integration of 0 to 2a f of x dx equal to integration of 0 to a f of x dx plus integration of 0 to a f of 2a minus x dx. Improper integrals. Improper integrals are classified in two kinds. Improper integral of first kind. Integration of 0 to a to b f of x dx is said to be improper integral of first kind if a equal to minus infinity or b equal to infinity or both. Integration of minus infinity to 0 e power x dx. Improper integral of second kind. Integration of a to b f of x is improper of second kind if a and b are finite but f of x is infinite for some x belongs to a comma b. Okay, now next, some useful comparison of integrals. Integration of a to infinite dx by x power p converges to 1 by p minus 1 into a power p minus 1. 1 p minus 1 to a power p minus 1 is the denominator part when p greater than 1 and diverges to infinity when p less than or equal to 1. That is called the values.